we've observed that we can think of matrix multiplication as a function. So if we have a matrix, say this matrix here, for example, we can define a linear transformation T of x equals A times x. Now, ordinarily, this transformation should alter x on a pretty fundamental level. So, for example, suppose that x is -1, 1. And we apply this transformation to x. Here's where we begin. A times x puts us over here. So this vector x has basically two properties. It has a length and it has a direction. It's pointing this way. And doing this multiplication changed both those properties. Changed the length, changed the direction. Occasionally, however, you might have a vector whose direction is not changed. For example, let's let V be this vector here. Then we can multiply A times V like so. Well, here's a V on the graph, and it has this length and is going in this direction. And here is A times V. The length has changed, but the direction has not. Such vectors turn out to be quite special and have major applications in fields like differential equations and dynamical systems. Differential equations have their own class. Many of you have taken it. Dynamical systems we'll touch on briefly in this course. Now, multiplying this vector by this matrix did not change its direction. It only scaled its length. And of course, we have another way of scaling the length of a vector. That's where scalar multiplication gets its name. In particular, if we compare V to AV, this vector AV is twice V. So in this particular case, the matrix multiplication is the same as scalar multiplication. With this as our motivation, let's define the following. Let A be a square matrix. Then a vector V, and this vector has one restriction. It has to be non-zero. A non-zero vector V is called an eigenvector of this matrix if there is some scalar, and by tradition we use the Greek letter lambda here, such that A times V equals lambda times V. So this multiplication by a matrix is the same as multiplication by a scalar. Lambda, in this context, is called an eigenvalue of A. And eigenvalues and eigenvectors occur in pairs, so this is an eigenvector associated with this eigenvalue.